So today is the wonderful day that you get to learn about the mole. And the mole in chemistry is a very special unit used to represent the amount of substance. It's one of those SI units, and you get to abbreviate it if you'd like, MOL. You don't have to write the E. You're welcome. Now what this unit is just like the dozen. Okay, it's the chemist's dozen. If I ask you how many things are in a dozen, it's probably pretty quick that you can answer 12. Well, to a chemist, if someone asks them how many things are in a mole, very quickly we can say 6.02 times 10 to the 23rd representative particles. Yes, indeed. Now, this special number is known as Avogadro's number, named after Mr. Amadeo Avogadro, who first envisioned this concept. And it's a very big number. Um, 1 million is times 10 to the 6th. 1 billion is times 10 to the ninth. A trillion is times 10 to the 12th. So we're not even approaching 1 mole when we're talking about a trillion. Just one little antidote, but if I took 6.02 times 10 to the 23rd marshmallows, and your typical, let's make a s'more campfire, 1-inch cubed marshmallow, I could spread them out across the United States of America, and those marshmallows would be completely covering the USA 650 miles high. That's a lot of marshmallows. That's a very big number. Why is it so incredibly big? Well, it's because the particles that make up the matter that we deal with are very, very small. We need a lot of them put together in order to get to work with a visible amount of matter. If I put, for example, 6.02 times 10 to the 23rd atoms of hydrogen together, it'll only be 1 gram, and that's barely visible, barely a workable amount of matter. So that's why that number has to be so big, and that's why this number, the mole, is so integral to chemistry, because of the atoms and ions that make up virtually everything, and we're constantly working with that. So again, yes, this is the chemist dozen. Someone decided that 1 dozen things is going to be 12. Well, it was decided that 1 mole is going to be 6.02 times 10 to the 23rd. And like I showed you up here, representative particles. What does that mean? Well, representative particles are what makes up the substance you're working with. For example, if I'm talking about atoms, atoms make up our elements. So if I had 1 mole of silicon, I would have 6.02 times 10 to the 23rd atoms of silicon, because atoms are what make up elements. Well, of course, elements can get together and form compounds. One type of compound is a molecular compound. And so molecules are another representative particle. They make up molecular compounds. Water, for example, the most prevalent molecular compound on the planet, if I had 1 mole of water, I would have 6.02 times 10 to the 23rd molecules. And our other kind of compounds are ionic. And so when we're talking about them, we have ions, or formula units, that make up ionic compounds. Here you see a picture of sodium chloride. Unlike the molecules that are kind of lumped together, and if you remember this at all, they are sharing valence electrons through covalent bonds. Our ionic compounds, they get together in these ratio of ions and form these really nice crystalline structures. So here you see sodium chloride, very common ionic compound. It's a 1-to-1 ratio of positive sodium cations to negative chloride anions. So the formula unit is NaCl, and that's just the representative unit of an ionic compound. The ions are actually making the compound up. But again, we're just going to be using this as some labels and whatnot in some of the problems we do. We'll get into the more details about that stuff in a couple other chapters. But again, a dozen is 12. If I have a dozen chocolate chip cookies, I have 12 cookies. Okay, so for the chemists, 1 mole is 6.02 times 10 to the 23rd, and it can be ions, formula units, molecules, or atoms. So our very first practical application of the mole is going to be the mass of a mole, molar mass. This is one that we use constantly. And so in order to explain that, I'd like to first take a moment to talk to you about the dozen again, a unit we're more familiar with. So let's pretend that we have the dozen mass, and that would be the mass of 1 dozen of any substance. How many grams per dozen? Well, let's say I have a dozen pencils, 12 pencils, and I wanted to know, well, how much does a dozen pencils weigh? What would I do? I'd put them on the scale. So let me do that for you. Done. 66.64 grams. Well, how much does each pencil weigh? I'm sure you're thinking, I'll take that 66.64, divide it by 12, and get 5.55 grams. Excellent. Is it guaranteed that each pencil weighs 5.55 grams? Not so much. Okay, we can have different flaws in the different pencils, but that is the average mass. Much like our atoms. You know, every chlorine atom on this planet isn't the same. There are isotopes. So we are not guaranteed to always have the exact same atom in an entire sample of an element. So this is a good analogy so far, isn't it? Well, what we can do with some information like this, and I'll refer to this again as we go more and more with the mole. Let's say you have a question like this. What if we had 500 grams of pencils? How many dozen is that? Or how many pencils is that? Well, I could give you 500 grams of pencils and I could make you count that. Not as much fun. Same thing with our atoms. I can't make you count atoms. As much as I'd like to, you just don't have enough time in your lifetime to count atoms. So how can I figure out how many dozen is that? You're right. Take your 500 grams, divide it by how much a dozen is. So when I do that, I see that it is 7.5 dozen. How many pencils is that? Of course. 7.5 times 12 is 90. One other big application. What if I increased that number? What if I had 60 dozen, 720 pencils, and I was manufacturing that, and I needed to ship these out, and I need to know how much is this going to weigh? Well, we can use that information above again. There's a couple different things we can do. First, I could say, okay, 60 dozen. Each dozen is 66.64. So that's 3,998.4 grams. Excellent. Or you might say, hey, there's 720 pencils. Each pencil is 5.55. So the mass is actually 3,996 grams. Hey, wait a minute. Remember, we've got some flaws. When we're talking about the pencils, they're not all perfect, and this is a calculated average mass for those 12 pencils. So when we balloon it up to 720, we're going to get a little bit of differentiation, and that's okay. Same with the mole. When we start talking about 6.02 times 10 to the 23rd things, it's a standard, and we're just going to accept it and say, okay, that's an approximate amount, because we can never 100% be sure that exactly the mass of a mole of something. I hope that helps, and let's take a look at then the actual molar mass. The molar mass is the mass of a mole of any substance, grams per mole. You can write the E if you'd like. What we're going to be getting, where we're going to get this information from is the periodic table. Those lovely red numbers on our periodic table, the atomic masses. Yes, when we were doing calculations and of atomic masses, we said AMU, atomic mass units. They're actually the molar masses. So if you look at the periodic table, here's a couple of examples. Oxygen says 15.9994. What that means is if you got 6.02 times 10 to the 23rd atoms of oxygen together, they would weigh 15.9994 grams. Excellent. Well, a lot of these numbers are a little crazy, so we have a classroom rule that we're going to round to the 10th. So I just wanted to review that lovely little topic with you. So looking at oxygen here, 15.9994. How I round, 15.9, that's the 10th spot. The next number says round up. And so the actual molar mass for us for oxygen is 16.0. Yes, you need the point 0. That means I'll take off points if you don't have it. That's just a rule we're going to use. Let's look at the next one. Iron. Iron, 55.845. Some people try to round backwards. They'll say, okay, well, the 5 makes the 4 a 5, which makes the 8 a 9, which makes this 56. Wrong. We start from the left. 55.8, and then 4, that means drop it like it's hot. And the molar mass for iron is 55.8. Two other examples, phosphorus, 30.97376, so 30.9. The 7 says round up. So we end up with, again, 31.0. And the last one, which always seems to give people fits, bromine, 79.904. 79.9, drop. I guarantee no matter how many times I say it or how hard I try, people are going to write bromine as 80.0, but it's 79.9. So these are the molar masses of the elements, and obviously the elements come together to make compounds. So how do we get the compound formulas? Well, the formulas for now I'll give to you. Like here's lithium chloride, LiCl. So all we got to do is find the molar masses of lithium and chlorine and add them together. So when I go to the periodic table, lithium is 6.9, chlorine is 35.5. You round them separately first and then add them together. So the molar mass of lithium chloride is 42.4 grams per mole. Some compounds will get a little more complex. Here we have aluminum sulfate. So what that means is aluminum sulfate is made with 2 aluminums, 3 sulfurs, and 12 oxygens. You have to do to the parentheses what you do in math class. So the 2 aluminums are out here, the 3 goes in, 3 sulfurs, and 12 oxygens. What that means mass-wise, the aluminums are 27.0, 2 of those, that makes 54. Sulfur is 32.1, 3 of those makes 96.3. And then there are 12 of the oxygen, 16.0 is 192. You add those together. So our final answer for the aluminum chloride, I'm sorry, for the aluminum sulfate is 342.3 grams per mole. We'll see some that get into the 400s and whatnot, but if you ever get a number in the thousands, probably means you multiplied these numbers together instead of adding. So just be careful with that. I'm going to show you the answers to the practice for the molar masses. So again, hopefully you try them first before perusing the answers. Here's the first half of the page. And again, noting when a point 0 is needed, it must be included. Pause the video if you need more time there. And this is the second half of the page. Again, point zeros when necessary. And pause the video if you need longer here. Thank you very much.